Angular momentum. In physics, angular momentum, rarely moment of momentum or rotational momentum, is the rotational equivalent of linear momentum. It is an important quantity in physics because it is a conserved quantity. The total angular momentum of a closed system remains constant. In 3 dimensions, the angular momentum for a point particle is a pseudovector or xp. The cross product of the particle's position vector are relative to some origin and its momentum vector. The latter is p equals mv in Newtonian mechanics. Unlike momentum, angular momentum depends on where the origin is chosen, since the particle's position is measured from it. Just as for angular velocity, there are 2 special types of angular momentum of an object. The spin angular momentum is the angular momentum about the object's center of mass, while the orbital angular momentum is the angular momentum about a chosen center of rotation. The total angular momentum is the sum of the spin and orbital angular momenta. The orbital angular momentum vector of a point particle is always parallel and directly proportional to its orbital angular velocity vector O, where the constant of proportionality depends on both the mass of the particle and its distance from origin. The spin angular momentum vector of a rigid body is proportional but not always parallel to the spin angular velocity vector O, making the constant of proportionality a second-rank tensor rather than a scalar. Angular momentum is an extensive quantity, i.e. the total angular momentum of any composite system is the sum of the angular momenta of its constituent parts. For a continuous rigid body or a fluid, the total angular momentum is the volume integral of angular momentum density, i.e. angular momentum per unit volume in the limit as volume shrinks to 0 over the entire body. Torque can be defined as the rate of change of angular momentum, analogous to force. The net external torque on any system is always equal to the total torque on the system. In other words, the sum of all internal torques of any system is always 0. This is the rotational analog of Newton's third law. Therefore, for a closed system where there is no net external torque, the total torque on the system must be 0, which means that the total angular momentum of the system is constant. The conservation of angular momentum helps explain many observed phenomena. For example, the increase in rotational speed of a spinning figure skater as the skater's arms are contracted, the high rotational rates of neutron stars, the Coriolis effect, and the precession of gyroscopes. In general, conservation limits the possible motion of a system, but does not uniquely determine it. In quantum mechanics, angular momentum, like other quantities, is expressed as an operator, and its one-dimensional projections have quantized eigenvalues. Angular momentum is subject to the Heisenberg uncertainty principle, implying that at any time only one projection, also called component, can be measured with definite precision. The other 2 then remain uncertain. Because of this, the axis of rotation of a quantum particle is undefined. Quantum particles do possess a type of non-orbital angular momentum called spin, but this angular momentum does not correspond to a spinning motion. Definition in classical mechanics. Orbital angular momentum in 2 dimensions. Scalar angular momentum from Lagrangian mechanics. Orbital angular momentum in 3 dimensions. Orbital angular momentum in 4 or more dimensions. Angular momentum in higher dimensions can be defined by application of Noether's theorem to rotation groups of higher order. Generalization beyond 3 dimensions is best treated using differential forms. Analogy to linear momentum. Angular momentum and torque. Conservation of angular momentum. General considerations. Relation to Newton's second law of motion. In Lagrangian formalism. In Hamiltonian formalism. Angular momentum in orbital mechanics. Solid bodies. Collection of particles. Single particle case. Case of a fixed center of mass. Angular momentum in general relativity. Angular momentum in quantum mechanics. Angular momentum in quantum mechanics differs in many profound respects from angular momentum in classical mechanics. In relativistic quantum mechanics, it differs even more, in which the above relativistic definition becomes a tensorial operator. Spin, orbital, and total angular momentum. The classical definition of angular momentum as L equals R X P backslash display style backslash math L equals backslash math or backslash times backslash math P if 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 P can be carried over to quantum mechanics by reinterpreting R as the quantum position operator and P as the quantum momentum operator. L is then an operator, specifically called the orbital angular momentum operator. The components of the angular momentum operator satisfy the commutation relations of the Lie algebra Sothry. Indeed, these operators are precisely the infinitesimal action of the rotation group on the quantum Hilbert space. See also the discussion below of the angular momentum operators as the generators of rotations. However, in quantum physics, there is another type of angular momentum called spin angular momentum, represented by the spin operator s. Almost all elementary particles have non-zero spin. Spin is often depicted as a particle literally spinning around an axis, but this is a misleading and inaccurate picture. Spin is an intrinsic property of a particle, unrelated to any sort of motion in space and fundamentally different from orbital angular momentum. All elementary particles have a characteristic spin possibly zero. For example, electrons have spin 1/2. This actually means spin h/2. Photons have spin 1. This actually means spin h. And pi mesons have spin 0. Finally, there is total angular momentum J, which combines both the spin and orbital angular momentum of all particles and fields. For one particle, J equals L plus S. Conservation of angular momentum applies to J, but not to L or S. For example, the spin-orbit interaction allows angular momentum to transfer back and forth between L and S, with the total remaining constant. Electrons and photons need not have integer-based values for total angular momentum, but can also have half-integer values. In molecules, the total angular momentum F is the sum of the raw vibronic orbital angular momentum n, the electron spin angular momentum s, and the nuclear spin angular momentum I. For electronic singlet states, the raw vibronic angular momentum is denoted J rather than n, as explained by van Vleck. The components of the molecular raw vibronic angular momentum referred to molecule fixed axes have different commutation relations from those for the components about space fixed axes. Quantization, uncertainty, total angular momentum as generator of rotations. Angular momentum in electrodynamics, angular momentum in optics. History. Newton in the Principia hinted at angular momentum in his examples of the first law of motion. Atop, the greater bodies of the planets and comets, meeting with less resistance in more free spaces, preserve their motions both progressive and circular for a much longer time. He did not further investigate angular momentum directly in the Principia. From such kind of reflections also sometimes arise the circular motions of bodies about their own centers. But these are cases which I do not consider in what follows, and it would be too tedious to demonstrate every particular that relates to this subject. However, his geometric proof of the law of areas is an outstanding example of Newton's genius, and indirectly proves angular momentum conservation in the case of a central force. The law of areas, Newton's derivation and innovation. As a planet orbits the Sun, the line between the Sun and the planet sweeps out equal areas in equal intervals of time. This had been known since Kepler expounded his second law of planetary motion. Newton derived a unique geometric proof, and went on to show that the attractive force of the sun's gravity was the cause of all of Kepler's laws. During the first interval of time, an object is in motion from point A to point B undisturbed. It would continue to point C during the second interval. When the object arrives at B, it receives an impulse directed toward point S. The impulse gives it a small added velocity toward S such that if this were its only velocity, it would move from B to V during the second interval. By the rules of velocity composition, these two velocities add, and point C is found by construction of parallelogram BCCV. Thus, the object's path is deflected by the impulse so that it arrives at point C at the end of the second interval. Because the triangles SBC and SBC have the same base SB and the same height BC or VC, they have the same area. By symmetry, triangle SBC also has the same area as triangle SAB. Therefore, the object has swept out equal areas SAB and SBC in equal times. At point C, the object receives another impulse toward S, again deflecting its path during the third interval from D to D. Thus, it continues to E and beyond. The triangles SAB, SBC, SBC, SCD, SCD, SD, SD all having the same area. Allowing the time intervals to become ever smaller, the path at A approaches indefinitely close to a continuous curve. Note that because this derivation is geometric, it shows that the law of areas applies to any central force, attractive or repulsive, continuous or non-continuous, or zero. Conservation of angular momentum in the law of areas. The proportionality of angular momentum to the area swept out by a moving object can be understood by realizing that the bases of the triangles, that is, the lines from S to the object, are equivalent to the radius r, and that the heights of the triangles are proportional to the perpendicular component of velocity v. Hence, if the area swept per unit time is constant, then by the triangular area formula 1/2 base height, the product base height, and therefore the product RV, are constant if r and the base length are decreased. V and height must increase proportionally. Mass is constant, therefore angular momentum rm is conserved by this exchange of distance and velocity. In the case of triangle SBC, area is equal to 1/2 SBVC. Wherever C is eventually located due to the impulse applied at B, the product SBVC and therefore Rm. Similarly so for each of the triangles. After Newton, Leonhard Euler, Daniel Bernoulli, and Patrick Darcy all understood angular momentum in terms of conservation of areal velocity, a result of their analysis of Kepler's second law of planetary motion. It is unlikely that they realized the implications for ordinary rotating matter. In 1736, Euler, like Newton, touched on some of the equations of angular momentum in his Mechanica without further developing them. Bernoulli wrote in a 1744 letter of a moment of rotational motion, possibly the first conception of angular momentum as we now understand it. In 1799, Pierre-Simon Laplace first realized that a fixed plane was associated with rotation, his invariable plane. Louis Poinsot in 1803 began representing rotations as a line segment perpendicular to the rotation, and elaborated on the conservation of moments. In 1852, Leon Foucault used a gyroscope. William J. M. Rankine's 1858 Manual of Applied Mechanics defined angular momentum in the modern sense for the first time. A line whose length is proportional to the magnitude of the angular momentum, and whose direction is perpendicular to the plane of motion of the body and of the fixed point, and such that when the motion of the body is viewed from the extremity of the line, the radius vector of the body seems to have right-handed rotation. In an 1872 edition of the same book, Rankine stated that the term angular momentum was introduced by Mr. Hayward, probably referring to R.B. Hayward's article on a direct method of estimating velocities, accelerations, and all similar quantities with respect to axes movable in any manner in space with applications, which was introduced. Rankine was mistaken, as numerous publications feature the term starting in the late 18th to early 19th centuries. However, Hayward's article apparently was the first use of the term and the concept seen by much of the English-speaking world. Before this, angular momentum was typically referred to as momentum of rotation in English. Footnotes: